Hello, ladies and gentlemen. We're going to do 4.4 today, the first and second fundamental theorem of calculus. The objectives are really long. We're going to use the first fundamental theorem of calculus to calculate the area under the curve. Then we're going to find the average value of a function over a given interval. Then we're going to use the second fundamental theorem of calculus, and we're going to do net change for displacement and total distance. And we're trying this in a new place, so we'll see how it works. All right, so if you will remember, an indefinite integral is going to be an integral without endpoints. And when I do an indefinite integral, it creates a family of functions. And if you'll remember, you get whatever you get when you integrate, but you always get a plus c. And so it translates those functions up or down. And so that would be your family of functions. The definite integral, on the other hand, starts from an endpoint and goes to another endpoint. And so it has a definite beginning and ending, and it's going to give you a specific value when you are done. And typically when we talk about integrating, we're talking about the area under our curve. Okay. All right, so then a couple other notation things to remember. If I have the integral from a to b of f of x dx, then remember that is whatever I get for the integration. F is the integration or the antiderivative evaluated at b minus f of a. So it's the top index minus the bottom index. And remember that capital F is the antiderivative. All right, so let's do an example. Okay. So I'm going to give you a curve. We're going to evaluate the integral from 0 to 2, absolute value 2x minus 1 dx. And it's always a good idea to look at the graph because it gives you specific information. So if I graph my little absolute value guy, he would look like this. And if I'm going to integrate from 0, I'm going to scoop that guy over to 2, then I'm going to have this area under the curve and this area under the curve. And that point of intersection is a half, right? And I could find that either algebraically or in my grapher. All right, so if you'll notice, because I have an area and then I have an area, I have two distinct areas, I'm going to split up the original integral. And so I'm going to split it up to be the integral from 0 to a half. And then because this is an absolute value function, this is the negative part of the piecewise. This is the positive part of the piecewise. So I'm going to evaluate the negative first, 2x minus 1 dx. And then I'm going to evaluate from a half to 2 of 2x minus 1 dx. So if I start doing all that math, remember I can take that negative out front. So here's a negative, 0 to a half, 2x minus 1 dx. And then I'm just going to evaluate this one from 1 half to 2 of 2x minus 1 dx. Alrighty, so if I do all of that math, and I'm assuming at this point that you can do that, I'm going to end up with, here's the negative, and I'm going to have 2x squared over 2 minus x evaluated from 0 to a half. And then I'm going to have 2x squared over 2 minus 1 evaluated from a half to 2. And remember, when you evaluate your indices, it's top minus the bottom. I'm assuming you can do this math. And, oops, that's an x. And then when I evaluate, I'm going to get 5 halves. So the area under the curve from 0 to 2 is going to be 5 halves. All right. Another thing that's really important to remember is the average value. So see if I can pull it down. There we go. The average value on an interval, and without proving it like we did last year, okay, and if I think about the average value, that might be the average height, because remember we're talking about summations of our rectangles. So that might be what my average value would represent. It's going to be 1 over b minus a times the integral from a to b of f of x dx. Okay, so that would be my average value on a specific interval. Okay, for our example, let's find the average value of the function f of x is equal to 3x squared minus 2x, and I'm going to do it over the interval from 1 to 4. All right, we have to pay attention to those words, average value. So my average value is going to be 1 over b minus a times the integral from 1 to 4 of 3x squared minus 2x dx. So remember, one of those little details that you always have to do when you're writing down your integration is to make sure that you put everything inside the integral in parentheses to show that this entire thing is being integrated with respect to x. If you don't do that, you don't get full credit. So this is 1 over 3 times the integral from 1 to 4 of 3x squared minus 2x dx. Well, if I do that math, here's the third. I'm going to have 3x to the third over 3 minus 2x squared over 2, and I'm going to evaluate it from 1 to 4. The 3's cancel, the 2's cancel, so this is 1/3 times x cubed minus x squared from 1 to 4. Alrighty. If I substitute those values in, I'm going to get 1/3. 4 to the third is 64 minus 16. And then if I do the 1, okay, it would be minus 1 and then plus 1. So that's your bottom index. Those two guys cancel. So this is 1/3 times 48, which is 16. And then remember, I need to report my answer as well. So I would say that the average value of the f of x is equal to 3x squared minus 2x is 16. Alrighty, the next thing that we're going to talk about is the fundamental theorem, the second fundamental theorem of calculus, because the first fundamental theorem of calculus just gets you the area under the curve. The second fundamental theorem is a little bit more entertaining. So this is the second fundamental theorem of calculus. All right, and that says if I want to take the derivative with respect to x from a to x of f of t dt, and if you remember from last year, we're using different variables to kind of illustrate the point. Well, when I take the derivative, I'm just going to get f of x. Okay, so that would say that the derivative of the antiderivative, which is kind of entertaining, is going to be f of x. All right, so I'm going to do an example and show you why this is true, because I think it might be a little bit easier to understand. So for the example, I want to find the derivative of, and I'm going to integrate from pi over 2 to x cubed of the cosine of t dt. Alrighty, so I'm going to go to a new page. When I get there, I want to do the derivative of the integral from pi over 2 to x cubed of cosine of t dt. Well, if I substitute in, if I just use the second fundamental theorem of calculus, then I'm going to get the cosine of x cubed. But because I'm taking the derivative of the top index, then I have to do the chain rule. It's 3x squared. And so then I would rewrite this as 3x squared times the cosine of x cubed. So that would be the derivative of the integral. But at this point, I have a weird shadow. I'm not sure what it's coming from. At this point, I want to show you how we got that so that you can understand how we get these values without actually having to do all the math. So let's go back and do this another way. So if I take the derivative of the integral, well, the integral of cosine is going to be the sine of t evaluated from pi over 2 to x cubed. Well, if I do that math, and I want to take the derivative, and I'm still evaluating the integral, I'm going to get the sine of x cubed minus the sine of pi over 2. And remember, I still have to take the derivative. Well, the sine of pi over 2 is 0. So now what I want to do is I want to take the derivative of the sine of x cubed. Okay? Well, the derivative is going to be the derivative of sine is cosine of x cubed, and then I have my handy-dandy chain rule times 3x squared. So this is 3x squared times cosine of x cubed. So the derivative of the integral gives me the same thing. What the second fundamental theorem of calculus tells you, if you understand this process, I actually don't have to do all this math, because that's a lot of math to have to do. Instead, I can do my direct substitution, but I do have to remember that if the derivative of that is something other than 1, then I also have to invoke the chain rule. Okay? This would be the reason as to why, but this would be the shortcut. And so that's what the second fundamental theorem of calculus does, is it gives you the shortcut. All right, the next thing that we're going to talk about is the net change. Okay? And we're talking about the total change, which is what net means, on an interval from A to B. So if I have a definite integral, and I'm going to have of the rate of change, which is the derivative of the antiderivative, this is going to equal the net change. So basically what that says is if I take an integral from A to B of f prime of x dx, I'm just going to get the antiderivative evaluated at B minus the antiderivative evaluated at A. Okay? So the net change then is going to be used in our displacement, and it could be used in total distance. So here's what I like to do when we talk about displacement. So let's say I start walking, and I walk this way, and then I go back this way, and then I go over here, and then I come back. Displacement would be from where I started to where I end, and it would be the distance between these two, except it would be a horizontal distance. Total distance, on the other hand, would be the sum. So if I walked this way some distance, and then back this way some distance, I would take this distance and add it to the second one, and then I would add it to the third one, and then I would add it to the fourth one. So even though I'm walking backwards, I'm still talking about how far did I walk total. Alrighty, so if we think about this, I can use these two concepts, and this one's actually really bad, so my bad. I'm talking about my total distance from point A to point B. Then we can talk about what happens when we talk about area. Okay? Let me go to another page. So let's say I have this handy dandy graph, and here is going to be my random function f of x, and I'm going to call this endpoint A, and I'm going to integrate to B. And so I'm looking at these different areas. This might be area 1, this might be area 2, and area 3. So if I wanted to talk about my total distance traveled, okay, this is a positive area, this is a negative area, and this is a positive area. So my total distance traveled would be the absolute value of A plus the absolute value of area 2 plus the absolute value of area 3. All right, that would be my total distance traveled. On the other hand, the displacement is where do I actually end up. So it's my actual ending location. Then if I were doing that with my areas, it would be the first area minus the second area, since it's negative, added to the third area, and then that would be my displacement. So displacement means if I start in one place, where do I end up? See? All right, so now let's do this algebraically with some lovely calculus. So if I have a particle is moving along the line so that its velocity is going to be v of t is equal to t cubed minus 10t squared plus 29t minus 20. And I want to ask a couple of different questions. So the first question would be, what is the displacement? From 1 to 5. Well, total displacement is just the sum of all the areas. If it's above the x-axis, it's a positive area. If it's below the x-axis, then it's a negative area. Alrighty. So if I do that math, and I go from 1, I'm going to integrate from 1 to 5, so I'm going to write my displacement is equal to, and then I'm going to just integrate what I have because the integration of velocity is position. So then I'm going to integrate t cubed minus 10t squared plus 29t minus 20 dt. And remember, when you're writing these out, your variables have to match. If I do this math either by hand or in my grapher, then I would get that my total displacement is 32 over 3. And that would be, because it's positive, I would go 32 over 3 units to the right, meaning that the net effect is from my beginning location to my ending location. I move 32 over 3 units to the right. So my second question then would be, what is the total distance traveled? And we're going to use the same integral of time, so from 1 to t to 5. Well, it's helpful at this point to look at the graph. So if you were to put this in your calculator and look at it from 1 to 5, this would be 1, this is 4, and this is 5. Notice that at this point, because I have a positive area, I'm moving to the right. And notice that I have a negative area, so I'm moving to the left. So my total distance, okay, and I'm going to integrate it from piece to piece to make sure that I get where I'm going. Alrighty, so I'm sorry, my brain and my mouth aren't working at the same speed. If I integrate velocity, then it's going to sum everything together and give me my displacement. But on my total distance, I'm going to have areas where I go positive and negative. And so I'm going to integrate from 1 to 4, and then I'm going to integrate from 1 to 5. So my total distance is going to equal from 1 to 4, and I'm going to integrate my v of t dt. And then I'm going to, I had subtract, but I think I need to add the integral from 4 to 5, and then I'm going to do v of t dt, right? And at this point, I want to make sure that this is the absolute value because I am going to add that area. So let's talk about tricks on the calculator. And since mine was sitting in my backpack, I had to go fetch it. All right, so let's go back and remember some tricks from last year. So with the wicked glare, there we go. Now you can see that I've entered our equation into my calculator. So then I'm going to quit, and I'm going to clear what I have, and I'm going to do math 9, because math 9 is my integration, right? And I'm going to integrate, we said we're going to go, can you still see it? I think you can, from 1 to 4. And I'm going to integrate. I don't want to have to retype that whole equation, so I'm going to do second trace, except in this, I'm going to do alpha trace, and I'm going to hit y1, except I'm going to put it inside the function. There we go. There's y1, and I'm going to differentiate with respect to x, and I'm going to add it to the integral, math 9, from 4 to 5 of, and then I want to make sure that I get my absolute value. So I'm going to do absolute value, and then I'm going to do alpha y1, and then I'm going to do my dx, because that takes the absolute value, and I get 11.833. So my total distance is 11.833, and it's greater than the units that I traveled from my displacement. Let me just check and make sure I did my math right. 32. Yep. So my total distance traveled is greater than my displacement because I traveled to the right and then I traveled to the left. And by making this be the absolute value, then that manages my total distance. So I include what I did from the positive direction and what I did from the negative direction. Alrighty. Now, if the directions said you had to do it by hand, then of course you would have to integrate by hand. Your responsibility, if you do it in your calculator, is to show exactly which math you're doing, and then you could put that in your calculator. You do not have to write that you're putting in y1. All right, so let me just give us a brief review or a recap of the formulas that you've gotten today. We know that the average value, right, would be 1 over b minus a, integral a to b f of x dx. My second fundamental theorem of calculus, that's an M. This one is really nice because it actually saves you some time when you are integrating and then taking the derivative of the integral. So if I'm integrating from a to x of f of t dt, it's just going to equal f of x. The only caveat that you have to remember with the second fundamental theorem of calculus is that if the derivative of the top index is something other than 1, then you have to do the chain rule. Then we have net change, okay, and that would be the integral from a to b of the derivative, and this is just going to equal the antiderivative evaluated at b minus the antiderivative evaluated at a. Your displacement, which is where do you end up, and just as a side note, remember that the integral of velocity is position, okay, so you need to remember that little detail. So the integral from a to b of v of t dt is the area and the area and the area. It's just the sum of your areas. If it's above the x-axis, it's positive. If it's below the x-axis, it's negative. Total distance is going to be the integral from a to b, and then I have to take the absolute value v of t dt, and that is just the positive sum of all of the areas. And that's it for today. I will see you tomorrow.